Hello, my name is Batiuk and I want to share a presentation of the current article called A Realization of Visual Biometric Validation to Enhance a Guarded and Efficient Authorization for Intellectual System, which was created by Dmytro Dosyn and Batiuk. This research aims to delve into the realms of safeguarding enhancement and capability optimization within authorization procedure in intellectual system through the utilization of visual biometric validation. A different realization of the parallel neural network utilizing both the contrastive loss approach and the triplet loss approach were scrutinized. Subsequently, a neural network employing the triplet loss approach was implemented and trained. Following successful training and verification of the neural network's approach, it was seamlessly integrated into the intellectual system. The particular neural network is a special class of involved neural networks designed to solve comparison tasks. Its name arose from the similarity with the structure of pair twins, which have common roots, but individual characteristics. The main idea behind a paired neural network is to learn the similarity of difference amid two input patterns. Paired neural network architecture includes two or more similar subnets and contribute parameters. Figures show the encoding model on the left and the model of the full paired neural network on the right. Therefore, for robust work, it is worth using a more contemporary approach, such as the TLA, triplet loss approach. This is one of the types of loss algorithms that is often used in paired neural networks for training models to compare entities in a vector space. The basic idea of triplet loss is to ensure that vector forms of similar entities are close together, while vector forms of different entities will be separated in space. The loss approach accepts three samples, both a positive and a negative sample for a particular entity, as well as a negative sample for another entity, trivially negative. The goal is to reduce the distance amid the vector forms of the positive and the anchor, trivially negative pattern, and the attempt to increase the distance amid the vector forms of the anchor and the involved negative pattern. Figure on the left show a conceptual model of the triplet loss approach, which contains a key input anchor as well as positive and negative entities at the input, and figure on the right shows a paired neural network model with an added triplet loss approach. The model can be used for a variety of tasks, such as face identification, entity extraction, or pattern identification, which is just a right our situation, since we need one file format for working with user photos and extracting user faces. There are also certain disadvantages of the paired neural network with a triplet loss approach. Namely, the model can be sensitive to the choice of hyperparameters such as the size of triplets and parameters of the triplet loss approach, as well as the dimensions of each layer, and the input parameters of the paired neural network with a triplet loss approach are given in the table which you can see below. Conversely, like many other models, paired neural network may be susceptible to overtraining, particularly when dealing with limited data. This consideration becomes crucial throughout the realization of paired neural networks, influencing both network architecture decisions and dataset selection for robust model training. Striking a balance amid the involvement of the model and the available data is pivotal to achieving optimal performance and avoiding issues related to undertraining or overtraining. Figure shows the detailed structure of the paired neural network with triplet loss approach, the size of each layer, and its input parameters. Figure on the left shows a block diagram of the approach of the initialization of two-aspect authorization of the user in the intellectual system by taking a photo, exploring for a face, and then saving the media key in the database. Figure on the right shows a diagram of the user authorization process, namely validation of the entered login and password, saving in local maintenance the user photo taken with the help of the web camera, and contrasting the current photo with the one already available in the database containing the user facial data. In case of successful match science, the user of the intellectual system gets access to the available approach. This figure illustrates a sequence diagram with an intellectual system delineating the interactions among three principal entities: the user, the server, and the database. Their communication is facilitated through HTTP requests, with each request possessing a listing context derived from its type and synchronization properties, executed in a specific order. The diagram provides a visual representation of a dynamic flow of interactions, showcasing the orchestration of action among the entities throughout the authorization process. As the user initiates actions, such as submitting login credentials or capturing a photo with a web camera, corresponding HTTP requests are generated and transmitted to the server. The server in turn processes these requests and interacts with the current database to retrieve or store all needed relevant information. Throughout the research process, a pivotal entity is the development of a parent neural network, centrally integrated into an intellectual system following rigorous testing. The realization leverages the Python 3.10 programming language for machine learning, and the PyCharm IDE was selected as the coding environment. The initial step involves acquiring a data set comprising photos paired with corresponding user labels, serving as the foundation for training and evaluating the neural network. Figure provides a complete overview of the dataset, encapsulating critical information such as the total number of images, unique user elements, and the pixel dimensions of each image. The following program approach is used to display 10 face images for each specified unique identifier. The images are displayed in the form of a grid, where each row represents one user from the dataset, and for each subject. 10 of these photos of different types are displayed, in which the user facial data is depicted differently and displays all unique emotions. This is shown in a figure below. Figure on the left illustrates a plot depicting the projecting of individual faces onto a plane through the implementation of the principal component analysis technique. Upon launching an approach to acquire the image coding model, this subsequent step involves implementing an approach to drive parent neural network right from the coding model and incorporating a specialized distance layer. The resultant parent neural network model underwent throughout testing and evaluation. Figure on the right provides insight into the classification results through the feature extraction technique, leveraging the distances amid encoded images. The graphical representation introduces a disparity matrix, facilitating the assessment of the model classification performance. Figure on the left appears a plot speaking to a band where x-axis appears completeness and y-axis appears exactness. Figure on the right appears an illustration of the comparison in the midst of a state picture and the input closeness check approach. As can be seen from the plot, the two photographs contain the same client, so the expectation is positive. Figure on the left shows the first step of user authorization in the intellectual system by entering a login and password. Figure in the middle shows the basic two-aspect authorization start page, and figure on the right shows turning on the user webcam and taking a photo of the user's facial data of the intellectual system. Figure on the left shows the process of processing the previously created paired neural network photo and exploring for a face on it. And figure on the right shows the result of successful face search in the photo and highlighting a certain face in green the area of the image where the user facial data was found. Figure on the left shows a comparison of the user's current photo taken using a webcam and a photo stored in the database. As a result, the prediction of the parent neural network is positive and the user was successfully authenticated to the system. Also, figure on the right shows the current user attempt to log into another user account in the intellectual system. Accordingly, the prediction of the neural network is negative and the user was refused authorization. The plot and figure speak to the reliance of preparing loss on the number of cycles, all through demonstrate preparing. Each point on the plot speaks to the loss at a particular emphasis. The plot shown in figure displays the main metrics for the user face identification model. Average precision is a measure of how well the model recognizes positive pairs that should be similar. A high p-value indicates the robustness of the model and identifying similar faces. Average negative, this value indicates the degree of similarity for negative pairs that should be different. A low AN value indicates the robustness of the model in identifying different faces. The last metric is test precision, which is the probability of a correct classification determination according to the test data set. The plot helps to evaluate three main aspects of the current model's performance for a specific determined face identification task. In the process of research, the development of an authorized system derived from visual biometric validation using a parent neural network, a complete analysis of aspects of safeguarding and robustness of the authorization process in intellectual system was conducted. An important step in the research was a consideration of substitutes to the realization of the parent neural network using the contrast loss approach and the triplet loss approach. The integration of the parent neural network into the intellectual system made it possible to create a robust means of identifying the user facial data, storing and contrasting the received data throughout authorization. This approach minimizes the risk of illegitimate access and guarantees the safeguarding of user accounts. Therefore, the development system is a robust and guarded tool for user authorization, capable of minimizing safeguarding threats in intellectual system. This approach can be used to improve the protection of confidential information and ensure reliable system access control. Thank you for your attention.